It's a great honor, not to mention inconsiderable burden to present what is. I'm only going to stick to the early history of theoretical chemistry in Cambridge, and it turns out that many of the concepts and ideas that we every day deal with actually originated with the work of a very small number of people, often lost in the midst of time. So it's good to be reminded of that, and I'll try to give you a flavor of what was an incredibly exciting period immediately after the discovery of quantum mechanics, and how a theoretical chemistry came to be shaped by John Lennard-Jones, Sir John Lennard-Jones, who was the first professor of theoretical chemistry, not just in Cambridge, but anywhere in the world, and a small group of his students. I've only got here a few of them, but I'll be mainly talking about the work of Coulson and Boys today. But it's kind of interesting to see the lineage, the doctoral students whom they went on to train. And one of them is Christopher Longard-Higgins, who was a PhD student of Coulson's when Coulson was for a brief period at Oxford. And Longard-Higgins succeeded Lennard-Jones as the second professor of theoretical chemistry. Now, you might see some interesting names here. One of them you see is Peter Higgs of the Higgs boson. And actually, Higgs did his PhD on molecular vibrations with Coulson when Coulson was professor of theoretical physics at King's College London. Another interesting name you see is Geoffrey Hinton. Now, it turns out that Longard-Higgins left theoretical chemistry in 1967 and went up and set up a new institute to study intelligence. And one of his early students was Geoffrey Hinton. And as we know, Hinton won the Nobel Prize, only was it last year, on artificial neural networks. And so if Kieran, you recall that Kieran mentioned that maybe one day large language models might come to save the day, save electronic structure theory, then you can see there's a beautiful symmetry here, and everything ends where it started. And I'm sure Lennard-Jones would be very happy to see that. But so after Longard-Higgins, the next professor of theoretical chemistry was David Buckingham, who was a PhD student of John Pople's when Pople was in Cambridge. So let me just, before I get on with the science, just mention just a few names of how things developed. Jean-Pierre Hansen, famous in liquid state theory and soft condensed matter, succeeded David Buckingham. And after Jean-Pierre was Dan Frenkel, also in soft condensed matter. And Angelos is today the present 1968 chair of theoretical chemistry. And I should mention here Ruth Linden-Bell, who was for many years the only woman in theoretical chemistry, and Ruth was my PhD supervisor. And I'm very happy also to say that Alex Thom, who did his PhD with me, he was appointed, well, he was made a professor here only recently, actually. So congratulations to Alex. And of course, there are others, Michiel Sprick and Michele, whom were appointed under Jean-Pierre, Rob Jack, Lucy Colwell, Rosanna, and Alex. I think this, together with David Wales and Stuart Althorpe, now represents the theoretical chemistry group today. But so this is actually moving forward in time, but it's interesting also to move backward in time to see who was Lennard-Jones's supervisor. That turned out to be a very influential mathematical physicist, Ray Fowler. And Fowler's PhD students included some interesting individuals, none less than Dirac, And Dirac and Lennard-Jones were exact contemporaries here, even though Lennard-Jones was a bit older. And I'll come to that in a second. And he may have had, and Dirac may have had a very important influence in bringing Lennard-Jones back. You can see Neville Mott and Chandrasekhar. So I guess there are not many people who can actually claim that they had 3 Nobel laureates among their PhD students, but Fowler is one of them. Okay, so everything that I'm going to be saying about Lennard-Jones can be found in this wonderful article by Neville Mott on Lennard-Jones and the biographical memoirs of the Royal Society. And it actually tells you what a different world it was in those days. Lennard-Jones actually specialized in classics. And he entered University of Manchester to study classics and then decided to switch to maths. I mean, that is something that you could do in those days. I'm not sure if it could be done nowadays, but anyway, that was in 1912. And then in between, he must have got his degree in 2015. He saw 3 years of war service. He entered the Royal Flying Corps, and he actually got his wings in 1917. I don't know if he actually saw actual aerial combat, but anyway, there it is. And then he returns to Manchester in 2019, and he immediately becomes a lecturer. And he also takes his DSc. I mean, he doesn't even get a PhD. He goes straight for a DSc immediately, working on vibrations in gases. And in Manchester, he meets a very eminent applied mathematician, Sidney Chapman. And Chapman suggested, you know, why don't you go to Cambridge? So he applies for an 1851 exhibition, and that gives him the opportunity to come to Cambridge, where he meets Ray Fowler, and he starts to work with Fowler, and he starts to get interested in interatomic forces. And in 1924, you know, he publishes, you know, this famous NM potential, and N and M were not known, and you know, he looks through the literature at the time, and he decides that, you know, this repulsive bit should be about 13, and this attractive bit should be 4. And that was on the basis of gas phase and solid state data that was available to him. Incidentally, if you want to look for Lennard-Jones's paper, you have to look under the name Jones, because he was called Jones. And then in 1925, he marries a Leonard and changes his name to a Lennard-Jones. So that is that. Now, he gets his PhD in 1924, and he's immediately appointed a reader in mathematical physics at Bristol. And in short order, he is actually, in 1926, appointed to full professor of theoretical physics in a specially created chair. Now, 1929 is a crucial year. He spends a year in Göttingen, and there he meets Heisenberg and Pauli, and he gets to learn about quantum mechanics. So he does not learn quantum mechanics from his PhD friend Dirac. But 1929 is a very important year. He publishes 2 papers, and one of the papers is on linear combination of atomic orbitals. So the concept of a molecular orbital goes back to Lennard-Jones. I mean, we use that method every day. And for many years, it was called the Hund-Mulliken-Lennard-Jones method. And in another landmark paper, which actually helps to convince experimentalists that quantum mechanics is not just, you know, some figment of some imagination, he actually publishes a paper on electronic structure of diatomic molecules, where he gives the first explanation of paramagnetism of the O2 molecule. Now, Lennard-Jones was, you know, he wasn't just a great scientist, but he knew about the importance of funding and getting funding. And so he actually raises funds and also to create a chair in theoretical physics, but also to fund some research positions. And his first 2 appointments to these research positions are none other than Hertzberg and Delbruck. So that really shows you the taste of the man. I mean, you know, to appoint 2 people who go on to win Nobel Prizes in the future. That is quite remarkable. Then he brings them to Bristol. Okay, now then in 1932, the university here receives a large gift by a plumber, and they decide to create a chair in theoretical chemistry. And although I don't know this, I guess Dirac would have had a major say in that. And Lennard-Jones returns to Cambridge, and he has a number of, absolutely stellar students, Coulson, Boys, and so on, that we're going to hear about. And now Chris Pickard mentioned today that Lennard-Jones also sets up here the mathematical laboratory, which then goes on to become the computer science department, and we'll see why that is. During the war, incidentally, Lennard-Jones returns to the military, and he actually plays a very, very important hidden role. He heads the armaments research establishment, which was, so Neville Mott's article covers this. It's, covers very important work. And then after the war, he returns to Cambridge, and he leaves in '53 to become essentially vice chancellor of what was to become University of Kiel. Okay, this is this a mechanical computer that he set up in 1938 to do quantum chemistry calculations. So now we come to his first PhD student, Charles Alfred Coulson, and an absolutely remarkable man. Coulson was actually a mathematician, and he initially wanted to work with Fowler, and he actually tells the story of Fowler returning from the first conference in quantum mechanics, and he says, "It was as though he had seen a vision. His eyes were aglow with it. He was unable to tell any of us students what it really amounted to, but quite evidently a new world had begun." Now, communications with Professor Fowler, however, was not easy at the best of times, especially when he went to the States for a period. So Charles looked around and almost by accident fixed himself up to work with Professor Lennard-Jones, just arrived from Bristol. Now, as an indication of what a period that must have been, it's written that this was, of course, an extremely creative period at Cambridge, which influenced Charles profoundly. One morning, he heard Dirac at a seminar discuss some mysterious properties of this, position momentum commutation relation. Charles asked at the end of the talk when the work had been done. Last night came the astonishing reply. So we think that we work in sort of in exciting times. We ain't seen nothing, basically. Now, his relations with Lennard-Jones were somewhat stiff at first. The professor was not very happy about Coulson's attire when attending supervision. Graduates engaged in postgraduate work, he wrote, are reminded that the supervisor is a university officer, no less. And when visiting officially in that capacity, they should dress as they would visiting any other officer of the university. Gowns, however, need not be worn in the chemical laboratory, so that's wonderful. Neither was Lennard-Jones too pleased by the infrequency of Charles's attendances, but soon he realized the powers of his student. And so now in Angelos, so if you visit Angelos, his office in Cambridge, there's a wonderful bookshelf of all of the PhD theses that have come out from the theory group, and the first 3 volumes are actually dissertations written by Coulson. So last week I went and picked this one. This is his PhD thesis, and there it is: Electronic Structure of Molecules, August 1936. And then he has various things: energy levels of the hydrogen 3+, energy levels of methane, interesting. And then this is what caught my eye: application of the self-consistent field method. Now, so in the preface, Coulson writes, this thesis devoted to discussion of electronic structure of molecules. It represents work done in Cambridge during the years 32 to 36 under the general guidance of Professor J.E. Lennard-Jones, FRS, to whom the author wishes to make acknowledgement. Then he says chapters 4, 6, and the first half of 5 have been suggested to the writer by Lennard-Jones. For the rest, except where expressly stated, the work may be presumed original. So in those days, the mere suggestion of a problem by your supervisor would render it unoriginal. But notice chapter 7 is not suggested by Lennard-Jones. So I turn to chapter 7, self-consistent field method. And there he says, the application of the self-consistent field to a study of molecular structure is inaugurated. So this may be the very first time anybody did an SCF calculation on a molecule. And then he says here, so this is very interesting, the SCF method of Hartree and Fock has been applied with some success to the study of atomic energies and wave functions. In this chapter, we discuss, we extend the problem to molecular structure. Now, this was like an absolutely incredible generalization because, of course, molecules, you have to deal with what I call multi-center integrals, far harder. And to imagine that, you know, there was no computing. He actually had to do all of these calculations, all of these integrals by essentially hand. It's a remarkable achievement. So some of the key contributions of Coulson, it turns out that the concept of a bond order and a fractional bond order actually go back to Coulson. And he gave the first, if you like, satisfactory definition that could explain the concept or the occurrence of aromaticity. So benzene, neither 1 nor 2. Another very interesting thing is energy bands in graphite, published in 1947. And so this got me intrigued. So I went and actually had a look at this paper, Energy Bands in Graphite. You can see 22nd of February, 1947, cited 53 times. Now, this is the first time anybody had ever written a paper showing A, you have a zero gap sort of system here, and B, you see these beautiful linear dispersions. This was first enunciated by Coulson, cited 53 times. I mean, imagine the thousands of papers that are published every year on graphene and graphite and what have you, 53 citations. So why is it that he didn't get cited very much? Well, the paper that is cited is this one by Wallace. You see May 1st, 1947. So actually, Coulson beat him. But it's actually, another point is that Coulson, did all of this work before the Second World War, but it was only published after the Second World War. So there are two lessons here. One is that it's probably not a good idea to wait 10 years roughly to publish something. That's one thing, although, you know, the World War took place in between. But the other interesting thing is that just because it comes out in Nature doesn't mean to say that it's going to have the biggest impact. I mean, so PhysRev here has its, so that's one thing. Now, there's another absolutely stunning contribution that that Coulson makes among many others, but one of them is explaining that there's an extra constant of motion in molecular systems, which mirrors the known extra constants of motion that exist in hydrogenic systems, where we know that you have an additional degeneracy among states of different angular momentum for the same principal quantum number. And Coulson treats an absolutely, it's this astonishing problem of two centers with different charges. And what he realized that if you take a hydrogenic system and you split it, the three additional constants of motion that are normally given by the Runge lens vector, two of them disappears, but one of them stays. And he figures out what that is. And this enables him to explain some very puzzling features of the H2 of linear system, whereby you get apparent violations of non-crossing rules. And it turns out that this additional symmetry enables that to occur. So Coulson, of course, is very famous for his work on the chemical bond, and I thought I should really mention this, Coulson's own description of the chemical bond, which is this. First, it is related to the disposition of two electrons, Remember, no one has ever seen an electron. Next, these electrons have their spins pointing in opposite directions. Remember, no one can ever measure the spin of a particular electron. Then, the spatial degree of these electrons is described analytically with some degree of precision. Remember, there is no way of distinguishing experimentally the density distribution of one electron for another. Concepts like hybridization, covalent and ionic structures, resonance, all appear, but not one of them corresponds to anything that is directly measurable. These concepts make a chemical bond so real, so lifelike, that I can almost see it. And then I wake with a shock of realization that a chemical bond does not exist. It is a figment of the imagination that we have invented, no more real than is the square root of -1. I will not say that the known is explained in terms of the unknown, but this is to misconstrue the sense of intellectual adventure. There is no explanation. There is form, there is structure, there is symmetry, there is growth, and therefore there is change in life. So that is Coulson. Now, what Coulson was actually talking about, he said that, look, basically you've got to solve the Schrödinger equation. The rest is essentially, well, is a figment of our imagination. And so this now brings me to the work of, brooding genius that was Frank Boys. So whereas Coulson, you read his papers, it's essentially like Mozart. It's very light and everything is beautiful and clear. And Boys, on the other hand, was very different. His papers are extremely difficult to read. And yet Boys essentially set the program for theoretical chemistry from essentially the 1940s to this day. Nick Handy, who was Boys's PhD student, actually mentions that had he not died at the relatively young age of 60, he would have almost certainly made the trip to Stockholm to receive his Nobel Prize. Now, unfortunately, Boys actually died a relatively obscure individual. He was a lecturer essentially till a few months before the end of his life, and then he was appointed a reader here, and he was actually elected shortly before his election, his readership, and then unfortunately he passed away. But so what was Boys's contribution? And so the first thing that Boys realized is that analytical work will take you so far, but ultimately you have to do numerical work, and he was absolutely set on that. And remember, this actually goes back to the 1940s. There were basically no computers as such, but he and one of the things that was preventing progress was the calculation of matrix elements between these exponential functions that Coulson and many others had tried to crack. And so he actually cut the Gordian knot, did Coulson, did Boys, and he said that, let's just represent our orbitals with Gaussians. It's the first time that Gaussian functions are used in this context, and the key is given in this diagram of his, and you see the key point is that you have these 4 center integrals that you have to evaluate, and what he observed is that if you take the product of 2 Gaussians, they give you, on different sites, that can be represented by a single Gaussian put in the middle. And so these 4 center integrals are then reduced to 2 center integrals, and then you can evaluate this, and you get the right answer. Now, Boys was obsessed with getting the right answer for the right reason. He was not afraid of making approximations, and the Gaussian was one such. And of course, he knew that the Gaussians are not ideal in shape and so on, but he decided to live with that. And one of the things that he introduced was to take linear combinations of Gaussians to approximate Slater-type orbitals. And one of Boys's landmark calculations, and this was one of the first times that theory was actually ahead of experiment was he predicted the ground state of CH2 to be a triplet with a bent geometry and not a singlet. And that was subsequently experimentally verified. Now, another absolutely incredible contribution of Boys is this very mysteriously entitled paper, Canonical Configuration Interaction Theory. But this is the first time that he introduces the idea of maximally localized orbitals. And he does it here. And these Boys orbitals, I guess, are what nowadays are called maximally localized Vanier orbitals in the context of molecular structure. But now I want to come to, what was an absolutely landmark paper, widely misunderstood, that Boys published together with Nick Handy on the so-called transcorrelated method. And this kind of shows you that Boys was simply not afraid of getting himself into very, very complicated theories. And he wanted to deal with correlated wave functions where electron-electron distances actually explicitly appear. People had tried to do that in a variational context, and that leads to horrible integrals that you can't really deal with. And Boys instead invented a Hamiltonian that he called the transcorrelated Hamiltonian, in which this correlation factor is wrapped in and brought into the Hamiltonian. Now, unfortunately, this Hamiltonian turns out to be both non-Hermitian and has three-body interactions in them. I mean, there's absolutely no way in 1969 they could have possibly dealt with this. But it turns out that this Hamiltonian is also wild Hamiltonian. It is very difficult to do numerically stable calculations with it. And for the past 60 years or so, people have tried very hard. And it's only very recently that we finally understood how to do this, how to tame the beast. And that's basically thanks to progress in QMC methods. And this is largely the work that my own group are doing in Stuttgart, where we show, using a transcorrelated Hamiltonian, you can now, using really very inexpensive calculations, obtain results that beat the state of the art using very relatively low-level theory. So those of you who are going to be in Trieste next week, I'll explain how this is actually done. Okay, how much time do I have? Not much. Well, let me just finish then by telling you of an absolutely fascinating story that I came across about Lennard-Jones's last PhD student, John Stanley Griffith. And so I was reading this, and I actually came across this work. John Griffith became quite well known in transition metal chemistry. And I was looking at iron-sulfur complexes and spin eigenstates there, and it turns out that he had done some work on that. And I started to look a little bit at this, and I found a really rather remarkable story that although he was Lennard-Jones's last student, Lennard-Jones had seconded him to go and work with Francis Crick. Crick was at the time, 1950-51, working on the structure of DNA. And so Crick had some idea that actually you have some sort of base pair stacking, and that's what causes attraction. So he asked Griffith to do some calculations on this, to prove Crick right. And Crick recalls the following, is that I suggested that like bases would attract each other and asked John Griffith to do the calculation. I was therefore very surprised when he told me later in the TQ at the Cavendish that he did not get attraction of like with like, but he did get attraction that A goes with T and G goes with C. Absolutely incredible. It was at this point that I said to him that this would immediately give complementary replication. He did not make that remark, although to me, looking back at it, it was obvious that he had thought of the idea himself. So this is an account that what has become known as Watson-Crick base pairing should actually have the name of John Stanley Griffith associated with it. So I had a look at this famous Nobel Prize winning paper of Watson and Crick. And of course, there is there an acknowledgement to Rosalind Franklin. We know about that scandal. But the name of Griffith does not even appear. It's absolutely incredible. Anyway, I shall end there.